Okay, I hope you're rested up and you're ready to finish the epsilon delta formal definition of the limit. What we want to talk about in this section is we want to actually use the epsilon delta definition of the limit to prove at least one of our limit laws. These are the ones that we learned in section 2.3, that the limit of a constant times the function is the constant times the limit of the function. The limit of a sum is the sum of the limits, and so on. Then we want to look at the formal definition of the one-sided limit, which is going to be a little different than the definition from both sides. What's different still is going to be the definition, formal definition, for an infinite limit when the y value goes to infinity. Let me share my screen with you and we'll get started. We're now going to talk about the proof of a limit law. Before we get into the actual proof, we need to review what a triangle inequality is. Maybe you've never seen this before, but I think it will make sense to you. It says the absolute value of the sum of two numbers has to be less than or equal to the absolute value of each individual number added together. Now, if the numbers are both positive, it won't make any difference. If the numbers are both negative, it won't make any difference. But if one of the numbers is positive and one of the numbers is negative, like say the absolute value of -7 plus 3, well, then we know that this would come out to be the absolute value of -4, which is 4. But if I were to take the absolute value of 7 plus the absolute value of 3, I would get 7 plus 3, which is 10, which is quite a bit larger. So we can see that taking the sum first may cause it to be smaller than if I took the absolute values of each individual number. We're going to need this in our proof. We're going to prove that the sum law for limits works. The limit of a sum is the sum of the limits. So if I have a limit of f of x as x approaches a of L, and a limit of g of x approaches the same number a, and this becomes m, then the limit of the combined function f of x plus g of x as x approaches the same number a should be L plus m. Let's prove it. Now, how are we going to prove that? Well, if you think about it, it's going to make perfect sense to you. I'm just going to make this be less than epsilon over 2, and this one be less than epsilon over 2. And then when I add them together, epsilon over 2 added to itself is going to give me epsilon. It works. Okay, so we're going to choose a delta 1 greater than 0, so that if 0 is less than x minus this a value in all three limits is less than delta 1, then f of x minus L is less than epsilon over 2. I choose a different delta for the g function so that when x minus a is between 0 and delta over 2, then the absolute value of g of x minus m is also less than epsilon over 2. Then I look at the two delta values and I do that trick I did on the more difficult proofs. I take the smaller one, choose the minimum of delta 1 and delta 2. Well, if they're the smaller one for delta, then it will work for both of these, which will guarantee that both are less than epsilon over 2. This means that 0, which is less than x minus a less than delta over 1, 0 less than x minus a less than delta over 2, implies that 0 less than x minus a is less than delta. And then I say that the absolute value of f of x plus g of x minus L plus m, I can rewrite these and reorder them so that I have f of x minus L and g minus m. Now I need that triangle inequality. I have the sum of two things inside an absolute value, which is less than or equal to the magnitude of each one individually in an absolute value. But I know that this first one is less than epsilon over 2, and the second is less than epsilon over 2, strictly less, and that adds up to epsilon. So I'm done, and I finish with QED. We now want to take a look at the one-sided limits and write those up in a formal way. When we look at a one-sided limit, remember that a one-sided limit means that x is approaching the value of a from one side only. From the left is from below, and we write a negative in the power position above a. From the right is from above, and we write a plus sign in the power position above a. In this case, we know which side of a the x is going to be on. So in the limit from the right, we know that x is to this is a, and this is x. So we know x minus a is already positive. I don't even need the absolute values, and it's going to be less than delta. So it replaces the one with the absolute values. Now, in the limit from the left, I know that if a is here, x is on the left side, coming this way towards a, which means x minus a is definitely negative. So it's less than 0, but greater than negative delta, which means a minus x is less than delta. And that will replace that part of the limit. Let's go ahead and look at the formal statements of the two one-sided limits. The limit from the right starts the same. Let f of x be defined over an open interval from a to b, where a is less than b. Then the limit as x approaches a from the right of f of x equals L if for every epsilon greater than 0, there exists a delta greater than 0 on the right, such that if 0 is less than x minus a less than delta, then the function value minus L magnitude is less than epsilon. We have a similar statement from the left. The only thing that changes is that f of x is defined over an open interval from b to c, where b is less than c. Then the limit as x approaches a from the left of f of x, and my c should actually be a. Ooh, I found an error in the notes. All right, there we go. If for every epsilon greater than 0, there exists a delta greater than 0, such that if negative delta is less than x minus a, which is negative because x is on the left of a, then f of x minus L is less than epsilon. Let's look at one example of a limit from one side only. We're going to be looking at the one which has the square root of 1 minus x. We know square roots are not defined when the radicand, the part under the radical, is negative. In this case, we have 1 minus x. Now, 1 minus x has been reflected and it's been shifted as well. So when we look at this one, realize that it's going to be starting at the value of 1 and then opening that way, right? So when we look at this particular one, we know that x can be negative and up to a maximum of 1. So it looks like this, right? So it's been shifted and reflected. So when I look at this one, I'm going to start the same way that I always start. It'll look a little bit different, not totally different, but mostly the same. I start with a being 1. My function is the square root of 1 minus x, and my L value is 0. I start with the square root of 1 minus x in absolute values minus the limit value of 0 less than epsilon. What am I trying to get? I'm trying to get at the bottom somewhere an x minus a, which is x minus 1. Same thing I was trying to get before. So I'm trying to get down here to x minus 1 less than something. Okay, well, if I look at this, I can go ahead and rewrite this without the 0, and I come up with this expression. Now, I'm close to having my x minus 1, but not quite. I've got a square root in there, which I do not want. Okay, well, if I have a square root in there, what would that do? Well, the square root, I could square both sides. That would get rid of that. And then I have 1 minus x less than epsilon squared. I had to square both sides to get rid of the square root. Now, when I'm looking at this, it's close, but it's not exact. And the question is, what do I do about that? Oh, I factor out the negative 1. This is going to give me negative 1 times negative 1 plus x, which I can rewrite in a different order as x minus 1. And I pulled the absolute value of the negative 1 out. And what is the absolute value of negative 1? Yes. So in fact, it turns out that the absolute value of 1 minus x and the absolute value of x minus 1 are essentially the same. And that gives me my value that I'm looking for. It's going to be epsilon squared. Then I start the formal statement of the proof. Let f of x be the square root of 1 minus x and epsilon greater than 0. Choose 0 less than delta equal to epsilon squared, such that if 0 is less than the magnitude of x minus 1 less than delta, then, and we start at the bottom, x minus 1 less than delta, oops, somehow that became an epsilon, delta equal to epsilon squared. And then I can write the absolute value of negative 1 times the absolute value of x minus 1 less than epsilon squared. And then I can pull that negative 1 in on the inside. And I can write negative 1 times x minus 1 less than epsilon squared. Multiply that out to get my 1 minus x less than epsilon squared. Take the square root of both sides to get the square root of 1 minus x less than epsilon squared. And finally, you must put back in the value of L, which was 0. That last line is the punch line. Don't leave that off. I count off major points for that error. And then you rewrite the limit. The limit as x approaches 1 from the left, I believe, yes, has to be, of the square root of 1 minus x equals 0. And finish it off with QED. Let's turn our attention now to infinite limits. We've covered one-sided limits, so we should think about infinite limits. Infinite limits is what the y value is doing. The y value is going to infinity, or the y value is going to negative infinity. It could be at a vertical asymptote, or it could be at infinity, like the graph of x squared. On both ends of the graph, it goes up forever, right? In order to have this happen, we want those values of the function to get bigger and bigger and bigger as x gets closer to a. We are not going to have a requirement that the absolute value of f of x minus L is less than epsilon, because our f of x's don't get close to anything. They get bigger. What we do instead is we choose some arbitrary value m, and we say, okay, 10 billion, top that. And that's your job. Find a value for delta that makes the function value be bigger than 10 billion. Well, if that's not enough, try Googleplex. Your job is to find a delta that makes the function values close to a bigger than a googolplex, which is 100 to the 100th power, I think. Okay, now what we want to do is write up and look at the picture, write up the formal definition and look at the picture. Here's the idea. If I choose a larger and larger m value, you can find a smaller and smaller delta close enough to A so that you can beat that m value no matter what is chosen. You can always get larger. Here's the formal statement of the infinite limit going to positive infinity. Let f of x be defined for all x not equal to A in the open interval around A. Same as before. Then we have an infinite limit. The limit as x approaches A of f of x is positive infinity. If for every m, ginormous number you choose, greater than 0, there exists a delta greater than 0, such that, and this is the same, 0 less than the magnitude of x minus A is less than delta, the y value tops that m value. F of x is greater than m. Here is the formal statement as we approach negative infinity. Let the function be defined for all x not equal to A in the open interval around A. Same. Then we have a negative infinite limit, meaning the limit as x approaches A of f of x is negative infinity. If for every m greater than 0, same, there exists delta greater than 0, same, such that if 0 is less than the magnitude of x minus A less than delta, same, then my function value gets lower than negative m, right? We can also define what it means for the end behavior to go to plus or minus infinity. Now, on the end behavior, it's a little bit different because end behavior means we're either approaching, x is approaching positive infinity or x is approaching negative infinity. In that case, we don't have a delta around an A because we don't have an A. We just have a direction, go that way. Okay, well then in that case, if you choose an m value and you say, this is my m value, top that, I have to be able to find a value on the x-axis whose y value gets above it. That proves that it goes to infinity. So in this case, I'm looking for an n. If for all the values of the function past n, they're all bigger than m, then I've proved it. And we have a similar one for going to negative infinity. In the case of negative infinity, you can say if for all negative, some big but negative number, there exists an n greater than 0, such that the function value gets even lower than m for all the x past n. Then you've proved it. We have similar definitions for the left side end behavior as well. Now let's take a look at this example, which is one of our infinite limits. I find that these are not terribly difficult. It would be a reasonable problem to have on an exam. And in this case, we're trying to prove that we have an infinite limit, positive infinity for the y value, at infinity, x approaching positive infinity, of the graph 3x squared, which you know looks like this, and on right side it goes up forever. I hope that's on your right as you're looking at it. So as you're, actually it looks like it's on your left. I need to change that. Okay, so when we're looking at this, we're gonna start over here and we're gonna say, we've got this n, and x is bigger than the n. Okay, and then I'm gonna try to build my function to be bigger than something so I can find it. So I need to figure out what n is. I'm focused on n. So I square the x and I square the n. Then I multiply both sides by 3, doesn't reverse the inequality. And then I notice that this means the function will be larger than 3n squared. Well, then I should let m be 3n squared. If m is 3n squared, now remember, we don't pick m last, we pick m first. I'm really trying to find the value of n. In that case, though, if I set them equal, I can solve for n. Remember that n is going to be a positive value because I'm going to positive infinity. So in this case, I solve for n and I get the square root of m over 3. So I've got the value of n in terms of m. And then I write the formal statement. Let m be greater than 0. Let n equal the square root of m over 3. Then for all x greater than m, we have the function 3x squared greater than 3n squared, which is 3 times the square root of m over 3 squared, which is m. Therefore, the limit goes to positive infinity. And we finish it off with QED. Let's talk for just a moment about limits that do not exist. What does it mean for a limit not to exist? If the limit doesn't exist, it's the last part of the definition that changes. The rest of it stays pretty much the same. The limit f of x as x approaches a does not exist if for every real number L, there exists a real number epsilon greater than 0, such that for all delta greater than 0, there is an x that meets the condition that it's close enough to a within delta of a, but the function value is not close enough to L. The magnitude of f of x minus L is greater than or equal to epsilon. Let's take a look at each part of that definition and translate it. For every epsilon greater than 0, there exists epsilon greater than 0, so that there exists a delta greater than 0. If x minus a's magnitude is between 0 and delta, then, and I've got an error here. All right, 2 errors. I'm going to have to fix that. F of x minus L, and this needs to be greater than equal to epsilon. There is an x satisfying this equation. Okay. I hope that this helps you to understand what the limit truly is. The limit is a difficult concept. It's not easy. It took almost 200 years for mathematicians to come up with a precise, formal, provable definition. It's not simple. It's quite complicated. Go ahead and use the template in order to help you to solve these problems. In the next chapter, we'll be looking at the derivative, and I think you'll find the derivative far easier than anything in section 2.5. Join me as we start the derivative in chapter 3.